welcome to this video on understanding interactions in the Cox model. So the focus of this lecture is going to be on interpreting parameter estimates. We're going to look first at interpreting parameter estimates in the main effects model, and then interpreting parameter estimates in interaction models. And we're going to talk about reparameterizing the interaction model. So the slides are available on my website. The examples that I'm going to show you use R, but Stata and SAS code are available on the same page as the slides. So, interactions between covariates. Well, in the introduction to the Cox model lecture, we assumed that estimated effects, that is the hazard ratios, are assumed to be constant across all levels of other covariates and constant over follow-up time. Now, this assumption applies in all regression models. There's an assumption that covariate effects are constant across all levels of the other effects unless you add interactions. So we're now going to study and relax this assumption by adding interactions. Now, in the Cox model, we're modeling the outcome as a function of time, so it's a little bit different from, for example, logistic regression and linear regression, because we assume the estimated effects are constant over both all of the other estimated covariates and time for which the effect is not actually estimated in the Cox model. Now, during this lecture, we're just going to look at the assumption that the covariate effects are constant for the other covariates. Studying that they are constant over time is slightly special because we don't estimate the effect of time, and that's the assumption of proportional hazards. So it's conceptually the same, but it's technically a little bit more difficult. And we're going to do this via an example. We're going to analyze survival for patients diagnosed with localized melanoma. The outcome is death due to melanoma, and we're going to focus on survival differences between males and females because there are interesting differences. Females do better than males. So we're going to estimate the hazard ratio for sex, females to males, and we're going to study if it varies by calendar period and age. Okay, so this is the main effects model. We're modeling the cancer-specific mortality as a function of sex, calendar period in two periods, 1985 to 1994, and then the earlier period is 1975 to 1984, and then age group, which is in 4 categories. So here are our parameter estimates, and we're going to focus on the parameter estimate for sex. Now, sex is coded as 1 for men and 2 for women. So in any regression model, the interpretation of the parameter estimate is it's the change in the outcome for a 1 unit increase in the explanatory variable. Now, a 1 unit increase in sex is the difference between men and women. So this coefficient here is the difference in the log hazard ratio between females and males while we hold period and age constant. Now, log hazards are not especially interpretable, so we typically look at the exponentiated coefficient, which is the estimated ratio of hazards for females to the hazard for males. That is the hazard ratio, while holding period and age constant. So here we see, after adjusting for sex and calendar period and assuming that they are constant, females have only 59% of the cancer-specific mortality of males, or females have a 41% lower mortality rate than males. And this is assumed to be the same in each and every age group. So, Females in age group 75 plus are estimated to have a 41% lower mortality than males in the same age group. Now, so here is what I just said on the slides. We're very shortly going to add an interaction between sex and period of diagnosis to see if the estimated effect of sex potentially varies between the two calendar periods. We'll start with calendar period because it's binary, so it's easier to do technically, but then age is more interesting from a biological standpoint. And there's also the assumption that the effect of sex is constant across follow-up time. That's the assumption of proportional hazards, and we'll look at that assumption in a separate video. So it's conceptually the same, but technically more difficult. So, to understand the interpretation of interactions, it's necessary to look at the mathematical formulation of the model. Now, we're going to look at a simplified model just with sex and period in it, but the concepts are the same if we also adjust for other covariates, such as age. So, let's imagine we have sex, which is x1, which is coded as 0 for male and 1 for female, and period, which is coded as 0 if you're diagnosed in the early period, 75 to 84, and 1 if you're diagnosed in the late period, 85 to 94. Now, when we're looking at interactions, it's much easier if our binary covariates are coded as 0 and 1, rather than 1 and 2. Now, when we fit the model, for each of the patterns of explanatory variables, and there are 4 patterns of explanatory variables, 2 by 2, so the model will give us a predicted value of the outcome, which is the logarithm of the hazard as a function of time for explanatory variables. Now we can see at the baseline level, when sex is male and period is the early period, where both of these are 0, this bit becomes 0. So the predicted outcome is just the log baseline hazard. And this is the definition of the baseline hazard. It's the hazard function as a function of time for individuals with covariates 0. Now, if we keep period at the 0 level, so this bit is 0, but we then go to females, then the predicted hazard function for females will be the log of the baseline hazard plus beta 1. So beta 1 is the additional log hazard for females compared to males. Now, I'm going to look at a table, and this is the main effects model, where for each of the 4 classes of patients in our data, this is the predicted value of the outcome. So when both covariates are 0, it's just the log baseline hazard. And then when we keep period at the 0 level, but we go to female, the predicted value of the outcome is the log baseline hazard plus beta 1. Well, what we can see is that, as I said before, beta 1 is the additional log hazard for females compared to males. And we can see by taking this bit minus this bit, we get beta 1. But beta 1 is also this expression here minus this expression here. So this is the difference in the log hazard for both of these two lines here are for the later period. X2 is 2, but it's the difference in the log hazard between females and males. So what we can see, beta 1 is the difference in the outcome, the difference in the log hazard between females and males, and it's assumed to be the same for both values of period. So beta 1 is the difference in the log hazards between females and males. It's the effect of sex, if you like, holding period of diagnosis constant, and it's the same for both the periods. And we can see when interpreting the estimated parameter effects, the baseline hazards cancel out. Now, if we had also adjusted for age, if we had adjusted for age in 4 categories, then there would be 16 combinations of covariates, or 16 classes of patients, but we would see exactly the same in the main effects model. The effect, the beta 1, would be the effect of sex, the difference between females and males, while holding both period and age constant. But I've made the model a little bit simpler. So this is the main effects model, and this is why the estimated covariate effects are assumed to be the same for all levels of the covariates. Now what we're going to do is we're going to add an interaction between sex and period. So we're going to create an additional explanatory variable x3, which is the product of x1 and x2. This variable will take the value 1 if you are both female and diagnosed in the later period. So if the sex variable is 1 and the period variable is 1, the interaction term takes the value 1. Otherwise, the interaction term takes the value 0. So let's have a look at the covariate and the parameter estimates. So we have x1 is for sex, x2 is for period, x3 is the interaction, and x3 takes the value 1 only when x1 and x2 are 1. Alright, so now let's have a look at beta 1. So if we take this expression here and subtract this expression here, well, this is beta 1. So exactly as we did before. So beta 1 is the effect of sex when x2 is 0. So we have females in the early period minus males in the early period. That's beta 1. So beta 1 is the effective sex for the reference level of period. Now, what if we want the effective sex for the other level of period? Well, we want to take the expression in the 4th row here, the effective sex in the later period, and then we want to subtract the effect for males in the later period. So we take the 2 rows in the later period, and we take females minus males. So this term minus this term, what do we get? we get beta 1 plus beta 3. So, the difference in the log hazards between females and males for the second calendar period is now beta 1 plus beta 3. So, the effective sex in the first calendar period, the early calendar period, was beta 1. The effective sex in the second period was beta 1 plus beta 3. The effective sex is no longer assumed to be the same for the other covariate in the model, which is period. And this is what we do when we specify an interaction. By modeling an interaction between sex and period, we are saying the effective sex now potentially differs for period. And the effective period also differs for sex. Now, what would happen if beta 3 was 0? Well, if beta 3 was 0, then the effective sex in this period here would just be beta 1. So the effective sex would be beta 1 in both periods. We would have constant effects. So beta 3 is the additional effective sex in the second period, or we can think of it as the difference between the two periods, between the difference in the log hazards between females and males. This is a technical definition. It's the additional effective sex between the periods. And we can do a formal test for is beta 3 0. So here we're fitting the model. We're putting in sex, we're putting in year, and we're putting in age group, and we're now adding the interaction effect between sex and period. Here are our parameter estimates. So, the estimates for the variable sex, now they look exactly the same. This row looks exactly the same as for the main effects model, but this hazard ratio here is no longer the effective sex, which is assumed to be constant across all other values. This is now the effective sex, but just for the reference level of period. Now, I've added age in this model. So this effective sex for the first period is the same for each age group in the first period, but this is the effective sex just in the first period. And this is what we went through when we looked at here. Beta 1 is interpreted as a difference in the log hazard between females and males, but only for the early period. So, what's the effective sex for the second period? Well, we have to add this coefficient plus this coefficient. So, this interaction coefficient is the additional effective sex. Now, on the original scale, we add them. On the multiplicative scale, we multiply them. So, this is the hazard ratio for sex in the early period. If we want the hazard ratio for sex in the second period, we have to multiply 0.60 by 0.94. So we get 0.699. So, one estimated effective sex for the first period, one estimated effective sex for the second period. Now, there's not a large difference. I wouldn't say this is a clinically significant difference, but we can also test for statistical significance. So if this coefficient was 0, which is equivalent to the exponentiated coefficient being 1, then the effective sex is the same for both periods. And we have here a test. Is the coefficient 0? So here we have p-value for the test of the null hypothesis that this parameter is 0. And there's no evidence against the null hypothesis. So there's no evidence of a statistically significant interaction. There's no evidence that the effective sex differs between the two periods. Now, we can fit the exact same model, but with a slightly different R syntax. So here we put in all of the main effects, and then we put in the interactions with a colon operator. We can also use the asterisk operator. The asterisk operator automatically includes all interactions and all main effects. Stata also has two different interaction operators. Stata has a single hash is equivalent to the colon, and a double hash is equivalent to the asterisk. So this is exactly the same model, but we're just using a slightly different syntax. Now, what we're doing here is we're fitting the same model, but with a different parameterization. So it's the same model, but the parameters have a different meaning. So this model that I've fitted here, it's identical in the sense that it has the same number of parameters, the same predicted values, the same likelihood function, but we've rearranged our data so that the parameters have a slightly different meaning. So in this model here, I got the effective sex for the baseline level of period, and then if I wanted the effective sex for the other period, I had to multiply this by the interaction parameter. Now, when we reparameterized, we're still getting the 0.60383, but instead of this, I'm actually getting the effective sex in the other period directly, which we calculated here to be 0.5699. I just went back a slide. So this is the reparameterized model. The effects of period and age group are all the same. Here we have the effective sex for the first period, but now, instead of getting the interaction term as the extra effective sex, we're now getting the hazard ratio for the effective sex. We're essentially asking Stata to multiply those two parameters for us. So if we're interested in estimating both of these hazard ratios for the effective sex, this model will give them to us. Now, what we don't get is we don't get a test of significance of the interaction. So now, this z-test here, now I seem to have deleted the p-value, but now I have the test statistic for the test of is the resulting parameter 0. So this Z statistic here, it is statistically significant, which means this hazard ratio here is statistically different from 1. This one here means this hazard ratio here is statistically different from 1. So, females do statistically significantly better than males in both periods. This is what this test statistic says. But we don't have a test of, is this number different from this number? Now, let's have a look at the two parameterizations. So here's the default parameterization. And here we have the alternative parameterization. And in the alternative parameterization, what our software is doing in the background is it's changing this 1 to a 0. And by doing so, what we now have is we have beta 1 is the effective sex when x2 is 0. So beta 1 is the difference between these. So we have one parameter which represents the effective sex for the 0 period, and the effective sex for the period when x2 is 2, the difference between this row and this row, the difference between this and this is now beta 3. So beta 3 now represents the effective sex for the second period. Now, we used our knowledge of how we specify models in R, but you could create 3 variables, x1, x2, x3, which look like this, and you would reproduce the regression output. So what I've done, I just went back a slide, is I used a sort of trick in how we specify models in R. This same trick works in Stata, and this same trick works in SAS. What I've done, I've put in age group that we're adjusted for. I've put in what looks like the main effective year, and I've put in the interaction between sex and year, but I haven't put in the main effect of sex. And this syntax gives us this parameterization. Okay, here is yet another parameterization. So here I've put in the interaction between sex and year, but neither of the main effects. I haven't put in sex or year. Now, what this gives us the effective sex and period compared to the joint reference group, which is females diagnosed in the latter period. So the coefficients now represent the difference in the log hazards between each of the 3 categories of sex and period compared to the joint reference group. So compared to females diagnosed in the later period, females diagnosed in the earlier period have a 44% higher mortality compared to females diagnosed in the late period. Males diagnosed in the late period have a 75% higher mortality. And this is the parameterization here. So we literally have one parameter for each of the 3 categories compared to the reference group. Okay. We're now going to look at the interaction between sex and age group. So, this is technically the same as what we were doing before, but we now have a 4-category variable for age. So let's put in year, age group, sex, and then sex by age group. Well, we're interested in sex. Let's look at the effect of sex. Here's the hazard ratio here, 0.49. Well, this is the effect of sex, but for the reference age group. And the reference age group is less than 45. If we want the effect of sex for the other age groups, well, we multiply it by the respective interaction term. So, the effect of sex for age group 45 to 59, we take the 0.49 and then we multiply it by 1.18. So, for age group 45 to 59, the effect of sex is 0.58. Now, why might the effect of sex depend on age? Can you think of a plausible biological reason? Well, if sex steroid hormones were implicated in the reasons for the differences, then we might see differences in survival between the sexes might depend on age. So if this was our hypothesis, then we might prefer an alternative categorization of age. We might prefer to categorize the patients into premenopausal, perimenopausal, or postmenopausal. So we don't have the best categorization of age if this was our hypothesis, but we'll go ahead and look at it anyway. So we can reparameterize using the exact same trick before to get the 4 hazard ratios for sex, 1 hazard ratio for each age group. And what we see, for the youngest patients, females do considerably better. Females have 51% lower mortality than males for the youngest. For the next age group, they have 42% lower, then 41% lower, and in the oldest age group, females still do better than males among the oldest age group, but the females only have 27% lower mortality. So the female superiority in survival depends on age. It decreases with decreasing age. Now, we can test this, but we're not testing one parameter like we were before. We have to test, are these 4 hazard ratios all equal? Or equivalently, if I go back to the default parameterization, I have to test. So this is our effect of sex for the baseline. These are the additional effects, if you like, in each of the other 3 age groups. So I would have to test jointly, are all of these 3 parameters here equal to 0? So we want to test with 3 degrees of freedom. So let's fit the model, and then we're going to test the linear hypothesis that this parameter, and this parameter are simultaneously 0. So here is our test here. The 3 interaction effects are 0. And we see, here's the test statistic, 3.7. Under the null hypothesis, this test statistic has a chi-squared distribution with 3 degrees of freedom. Here's the p-value. Well, we fail to reject the null hypothesis that the effect of sex is the same in each age group. So we have observed that the effect of sex depends on age, and the dependence is consistent with what we might expect if sex steroid hormones were the reason or part of the reason for the difference. So we see clinically interesting differences which are consistent with our hypothesis, but the differences are not statistically significant. And for completeness, I'm going to do a likelihood ratio test. I'm going to fit the main effects model. Then I'm going to fit the interaction model. And then we compare the likelihoods for the two models. So this is a conceptually identical test, but slightly different mathematically. The previous test was a wall test. We're now using a likelihood ratio test. The wall test is an approximation to the likelihood ratio test. So we would expect to get the same results. And we see that the test statistic and the p-value are similar, but not identical. Okay, that's the end of the lecture. Thanks for listening if you've made it this far.